Hi, ladies and gentlemen. We're going to move on to the next section, talking about open Newton-Cotes methods. So let's jump straight into the text. Looking here, we're on section 5.4, and as we discussed on the first day of quadrature, the Newton-Cotes methods are defined by the fact that they are equally spaced nodes. And so that's true for both the closed and the open Newton-Cotes methods. The difference is with open Newton-Cotes methods, we are no longer going to use an interpolating polynomial that goes all the way to the ends. And that is described in here along with how we gather up the nodes and determine what our h value is. So keeping track of the step size is an important piece of what we're doing. Here's the graphic that kind of explains the whole thing. We have some polynomial interpolant, which is represented by the red dashed line. And for the closed Newton-Cotes methods, we would go from x naught to xn, however many nodes we have. And that would be the end of our integral. In the case of open Newton-Cotes, what we do is we have the integral from a to b, and we are not including those endpoints in our quadrature development. We are going to step inside, and we're going to use the internal nodes in order to generate this type of quadrature method. So there's derivation here. The first three open Newton-Cotes methods are listed. The midpoint rule, which is derived up here, it's quite straightforward. And then we also have the open Newton-Cotes first order and second order interpolating polynomials. We're going to spend most of our time today talking about the second order interpolating polynomial to do a bit of a comparison with Simpson's rule and to give you exposure to how these things are derived. Remember, there will be a test question where you need to derive one of these methods. So first, what I would like to do is take a look at the open Newton-Cotes method here called the midpoint rule, which again, you're familiar with this from calculus. So what we have is we have an integral. Sorry about that, too many hotkeys. So we're going to take a look at the integral a to b of some function f of x dx, and we're going to approximate that using, like I said, a formula you learned in calculus. We're going to take 2 times f evaluated at the midpoint, which is b plus a over 2. And then we have the error term as well. So we have plus the h cubed over 3 f double prime evaluated at some value of xc. So I just want to lay out for you what we're looking at here. We have an interval a to b, but because it's open Newton-Cotes, what we've done is we've selected only a single node that is in the middle of the interval, right? That's the midpoint of the interval that we're using. And our interpolating polynomial here is just going to be a constant function. And we know when we have some function like this that we want to evaluate the integral of a to b on, it's reasonable to come up here and select that value and then multiply times the distance b to a. And so what I've forgotten in the formula is this h, because 2h, the h is defined as the distance from the endpoint to the node or between nodes. So that's an h and this is an h, which is why the evaluation is 2h times f at x naught. That is our approximation to the integral. What I'd like to do is take a look at what the degree of precision for this method is. If we are going to integrate a to b, f of x dx, and we're going to approximate that with 2hf at x naught, remember for degree of precision, we're going to transfer the integral to -1 to 1, and we're going to integrate functions, which are the monomials, the basis functions for polynomials, on that interval. And we're going to match up, and we're going to see how many integrals of monomials we have an exact match for. So starting, right, this is going to lead to degree of precision. And we're going to start with a constant function. So starting with f of t is 1, we're going to integrate negative 1 to 1, the function 1, which of course that integral is 2. And we're going to use our method here, which when we transfer it over to this construction, the h value is going to be equal to 1, and the x naught value is going to be equal to 0. So our calculations are always going to be 2 times f evaluated at 0. In the case where the function is equal to 1, the function evaluation, of course, is 1, and we have 2 times 1, which is 2. So at least we have degree of precision 0, because we can take care of constant functions. How about when we go negative 1 to 1 t dt? Integrating, remember that's t squared over 2. Any even number or even function integrated symmetrically across the y-axis is going to give us a 0. And we evaluate the function t at 0 times 2 is going to be 2 times 0, which is 0. So the midpoint rule is at least degree of precision 1. It takes care of all linear functions. So the next function to consider is a quadratic. And we integrate the quadratic and we end up with t cubed over 3 evaluated from negative 1 to 1, which is 2/3. And our function, we're going to take the function again, evaluating at 0, and that's going to be 2 times 0, which is 0. These are no longer equal. So we have a degree of precision of 1 for the midpoint rule. And this is how we would prove that. Continuing on then, let's take a look at this method here, which is using the parabola. We're going to discuss that in detail. So before we have that conversation, I just encourage you to read the quadrature error stability conversation, which basically tells us the opposite of what we see in numerical approximation error. So instead of being worse, like I discussed in class, integration is actually a smoothing operation. We try to integrate things because it sums out all of the noise that's in the system. We get, just like with round off, with floating point, we get the cancellation of the aboves and belows. So as we integrate functions that are bouncing up and down, we cancel out the aboves and belows and we get a smoothing operation on whatever we are summing. All right, so no further ado, let's take a look at this problem right here. So I have this PDF, which is talking about deriving the open Newton-Cotes method with, again, a parabola. And in this case, we have a different situation. We have a to b, where a is x naught and b is x4. So we're going to integrate the function from x naught to x4, just as we see down here. But we're not going to use these external nodes. We're going to only use the 3 nodes in the middle. We know that for 3 points that are non-collinear, we have a single unique parabola that goes through those, and that's what we're going to use. Just as we discussed in class, we can use the Lagrange interpolating polynomials. So we can build the Lagrange interpolating polynomials, which I have done. I've left off the error term because we're not going to proceed this way. But we end up in the same situation. In fact, it's a little bit more strenuous than what we were talking about in class, because we're going to be evaluating these quadratics at points that aren't even part of the conversation yet, at x naught and x4. So this method can be done. This will work, but it's tough. So instead of doing that, we are going to use Taylor series expansion, exactly the same as we did in class. In fact, I'm again expanding about the point x1. So in this case, note that we have 5 nodes, x naught, x1, x2, x3, and x4. So let me erase this and straighten it out. So we have these 5 points, and I'm going to expand about this one. That's a bad idea, and you'll see why in just a minute. The one that you want to expand about is x2. So when you do this problem as a homework problem, expand about x2, and I'll show you what the difference is going to be. So first things first, of course, we're going to build the Taylor polynomial. And we're going to, of course, implement the shorthand that we discussed in class, just to make things a little tidier so we don't have equations going edge to edge on the page here. And then we're going to set up and we're going to do this integration. So the part that would be different if you choose x2 is we would end up with an integral from minus 2h to 2h. And then, of course, it would be f at t plus x2. Remember the h part of it. That's 1h going backwards. That's 2h. This is 1h going forward, 2h. That's why the